used to balance out the weight of the mass, right? So that is okay. So that's just the propagation speed. And then, so we see here that if we set up the string like this, and then we just pick it up and we vibrate it, then the propagation, the pulse will be traveling with this speed. It is fixed by the characteristic, which is pretty nice. Now, we can, so now we know how to determine the speed. We can then look at the energy carried by the wave on the string, and that is a direct result of this. So if you think about it, each element of the string is oscillating up and down, right, in a wave. We have the sine or the cosine describing the position and velocity, and also the acceleration. Well, this just screams the mass spring system, right? And the energy configuration is very similar. This is just a bunch of mass oscillating, right? Each mass being each element of the string. So we know that if we have a little mass, say some mu delta x, which is a small element of the string with length delta x, it has mass mu delta x, right? Its total energy would just be 1/2 times its mass times the maximum velocity squared, right? Maximum oscillating velocity, right? This comes from the discussion in the mass spring system, right? The total energy is 1/2 times k times the amplitude square, or 1/2 times mass times v max squared, right? So we just do that, and then we know from this expression that Vy maximizes at omega a, right? Because cosine maximizes at 1. Then, as a result, this is just omega squared a squared, right? We have mu times delta x times 1/2. Then, in total, we see that the energy stored by the average energy stored by a string element over the period is this, right? And now, if the wave pattern is traveling at the speed delta, if it is traveling over this element delta x using the time delta t such that delta x is v delta t, right, the propagation speed, then we can just say that the rate of energy transfer by the string wave is just this guy divided by delta t, which means that we just change this to v. And that should be the rate of energy transfer, right? And we represent it by T here because it has the unit of a power, meaning that if the energy in the SI unit is in joule and T is in second, then P is in watts, right? Now, when we put all this together, we see the rate of energy transfer by the wave. We can try to do this example, which is just basically you are given all the parameter and plug things in. But since I need to wrap this up in 5 minutes, 6 minutes, I will skip this one for now. We can come back to it. But I think it's more worthwhile if we look at a household example of the longitudinal wave. So before, when we look at the string wave, this is just a transverse wave, right? Remember that the string element is moving up and down while the wave is propagating left to right. Well, here is an example of a longitudinal wave in which we have the gas particle in the chamber moving left or right, while the pattern also propagates from left to right. Now, this is actually a very simple model of a sound wave. So we start off with a gas chamber. So it is just a piston filled by some gas, right? And at one end we can freely move it up or down, right? We can compress it in, we can pull it out, right? And so essentially we are changing the volume of the container. And then when when we compress, when we move the piston in, meaning that we compress the gas, then we will get a lump of high pressure, right? Because the gas near the piston, it gets compressed, so it will have more pressure. And it is represented by a dark area here. And once we release the piston afterward, this dark area of high pressure, it keeps going actually, and it will keep going this way, propagating like a wave. And if we keep maintaining the pattern, we keep moving the piston in and out, right? Then you start to get a lot of high pressure bumps. And if we do it regularly enough, then we just get a wave of pressure, right? We have high pressure and low pressure alternating in a regular pattern, right? And that is the pressure wave, meaning that if we write this down mathematically, we just see that the pressure at some position x and sometimes t, it is just some average pressure, right, plus the amplitude delta p max times the sine function, like the wave on the string, right? And here the distance between the two high pressure regions, right? It is similar to the distance between the two peaks in the string, and that is exactly the wavelength lambda, right? So that is exactly the same concept. It is just a different physical quality that we are focusing on. Now we have the pressure wave looking like this. That's pretty straightforward, but then we can also write a corresponding displacement wave, meaning that for each molecule of gas in here, right, when you are right here, you have a high pressure region to the left, the low pressure region to the right. In order for you to contribute to this pattern, as a gas molecule here, you need to move slightly toward the left to clump in and make a lump around here, right? And then making this pressure a bit lower. And on the other hand, after some time, you are now here, right, and you have a high pressure region to the right, then you need to move a little bit to the right. So that means for each molecule of gas in the chamber, under this wave pattern, you need to keep moving left or right. And this is exactly why this wave of pressure is actually a longitudinal wave, right? Because the gas molecule is moving left or right with the displacement S, described by the cosine function here. The reason it is cosine and not sine is because you have to account for the fact that if your pressure is maximized or minimized, then your displacement is 0. But if your pressure is at the equilibrium P0, that is when your displacement is maximized, if you think about it, right? If you are right between a high pressure and a low pressure region, that is when you are forced to move the most toward the high pressure direction. So this S is the displacement in the x direction of a gas molecule, or rather an average gas molecule at each position x and time t, right? So if you have a gas molecule at x, its actual position at time t will be x plus s, right? Now this, as promised, this is a very simple example of a sound wave, because the sound wave is basically the change of air pressure that comes in wave pattern, like so. And actually the frequency, if you remember, which is related to 1 over the period, or it is related, or rather more generally, it is the propagation speed divided by the wavelength, right? That frequency relates to the pitch of the sound. So if you consider higher notes, then that means you are looking at a sound with higher frequency or lower wavelength. And also there is the wavelength of the sound, where there is the wavelength of the, if the wavelength of the sound is very high or very long, right, then the frequency is very low. And if the frequency is too low or too high, our ears cannot detect your sound. So our ears can only hear like a range of frequency. And for the sound with frequency too high, which means the wavelength too low, the pressure is changing very quickly in X. Then for those sound, our ears cannot hear, but we call it ultrasound, and it has other applications in medical science and more, right? You can just use it to scan for objects and stuff like that. So that means just some simple change of pressure is actually very useful. Now, the propagation speed of the sound is actually, it depends on the physical characteristic of the medium, which is the air, right? Or the solid, or whatever the sound is propagating on, right? It can be the wall, it can go to the wall too, right? Not this wall maybe. Now, if the propagation speed of the sound, it is basically just the square root of the ratio B divided by rho. Rho here is just the density of the medium, right? So if the sound is propagating in the air, just put in the air density here. But the parameter B here is a bit more involved. It is called the bulk modulus of the gas, which is it tells you how much the pressure has to change in order for the gas to expand or shrink the relative volume delta V over V, like so, right? Then with these two relations, this one is related. What is more important than the actual form is how it describes the gas, right? It basically tells you how much the gas expand or shrink given a change in pressure, right? So that's the physical characteristic of the gas, and so is the rho, which is also the density of the gas, the mass per volume, right? Both of them are physical characteristic of the medium, the gas. Now here with V and the lambda, we can determine the frequency of the sound. So that's same stuff as before, as the string wave, right? And last but not least, we can look at the energy transfer of the sound. So it is a very similar idea, right? You have some cross-sectional area A of the piston, in this case, this guy, right? The cross-sectional area A here. Then you have the maximum velocity, omega square S max square, right? And then you have the propagation speed. So that's the power transfer. And if we divide this by the cross-sectional area, then we get the intensity, right? And it is this intensity that gives us the loudness of the sound. So the higher the I, it means the more power, the more energy the sound transfer per minute, right? And that means we will feel that the sound is louder. And actually, we feel that in a log scale though. So if the sound is twice as loud, we will feel that the loudness increased by an increment. So that means we will feel if I increase from 1 to 2, we will feel the same difference as if I increase from 2 to 4 and so on. And this inspires the definition of what is called the decibel scale, beta, which is the 10 times the log of I divided by some reference number I naught, which is a constant. It is 10 to the minus 12 watt per square meters, and it is basically the minimum loudness that our ear can detect. Well, with all these equations, I think it is a lot of definitions, but what is more important is how it goes physically, and when we understand that the sound is simply just the vibration of the air, and the speed and all those characteristics are determined by how much the fluctuation is based on S max, and the speed is based on the characteristic of the gas medium. Then the rest is just you can look up the equation and then put things in when needed, right? So that is all I had to say about the sound, and then I guess that wraps up the discussion on the first part of the wave motion. Next time we will look at what would happen if we have several waves coming together, or if we have a wave and we hit the wall and it has to reflect and stuff like that, and see how it goes. So if there is any question, I would be happy to stay and answer. and otherwise have a good day.